Good morning or good afternoon, depending on where you are in the country viewing today's briefing. My name is Dwayne Brown with the Office of Public Affairs at NASA headquarters in Washington, D.C. The torch has been passed from NASA's Jet Propulsion Laboratory in Pasadena, California, to the University of Arizona's Lunar and Planetary Laboratory here in Tucson. Until further notice, briefings will originate from this location. I'll be your moderator for the next couple of days. Then I, too, will pass the torch to the laboratory's Public Affairs Manager, Sarah Hammond. This is yet another example of the incredible teamwork and partnership at all levels for the Phoenix Mars mission. Phoenix is preparing for what, quite frankly, is what it's all about, ladies and gentlemen, science. And who knows what the next 90 days will bring. We'll have presentations from our participants today, then we will open it up for questions starting here in Tucson, moving to the Jet Propulsion Lab, and then take questions via phone. Before we get started, let me introduce you to today's participants. First, to my immediate left, Mark Lemon, Surface Stereo Imager Co-Investigator, Texas A&M University. Robert Bonnetz, Robotic Arm Manager, NASA's Jet Propulsion Laboratory. And joining us from the Jet Propulsion Laboratory, NASA's own Superman, Barry Goldstein, the Phoenix Project Manager. And we are actually going to start with, there's Superman, there he is. We're going to start with Barry, who will give us the Phoenix spacecraft health and the supporting Mars spacecraft. Barry?
Well, I don't know how to respond to that, Dwayne, other than to say it's gotten very lonely over here. Where'd you guys all go? Let me give people a little bit of an update on how the spacecraft is. Let me start by saying the spacecraft is in excellent health, absolutely excellent health. And I know we had a bit of drama here yesterday relative to communication, but there never was an issue with Phoenix. Now that we've gotten to the point that we're on the surface and all the excitement of ADL has gone by, I'll calm down a bit and talk a little bit about how our surface mission operates, and that'll help explain the situation we're in and why what happened yesterday was never a big issue for us. When we're on the surface, since Phoenix is actually in the northern polar region, the orbiters, the Mars Reconnaissance Orbiter and the Odyssey Orbiter, actually pass overhead several times a day. Every 2 hours, each of the spacecraft are within view of one of our two UHF antennas that are on the lander. And the way we've organized and designed our operations on the surface is we actually define what we call our tactical mission, such that we have a very good pass in the morning, a very good pass with one of the orbiters in the morning, and a very good pass late in the evening. And the reason for that is what we do in the morning is we send up the commands that the science team and the engineering team had worked on the night before, and in the evening we get the data that basically was generated by the information that we sent up in the morning. And since we have such a rich opportunity of passes with the two orbiters to choose from, we basically choose which two look the best for that day, independent of whether it's Odyssey or MRO. And as it turned out, for yesterday's pass, the AM opportunity and the PM opportunity were both for MRO. In addition to those two passes, we have what we've affectionately called burp passes, which is basically what we're doing is very small passes that don't have as good of a margin as the others do, and what we do is we send back engineering information on those burp passes. Well, what happened yesterday is there was an anomaly on the MRO spacecraft where the radio reset just at the time of the AM pass. And as I said before, that's when we're sending information up to the spacecraft to do the operations we wanted to do for the day. And our intent that day, our intent yesterday, the prime activity was to start the deployment of the robotic arm that Bob's going to talk about later in this briefing. Well, because the uplink did not work, what the Phoenix spacecraft did, per plan, is it operates what we call our run-out sequence, which means if it doesn't hear its command in the AM pass, doesn't get the commands in the AM pass, it executes a sequence that's already pre-stored. We don't want to waste any of the precious days we have on the surface of Mars. And you'll hear Mike talk about all the images we took yesterday. So that AM pass, even though it didn't work, we were able to get good science yesterday. As it turned out, since we had the PM pass set with MRO, we were still listening for MRO in the evening. And sure enough, what happened was when MRO came over at the predetermined time, it turned out that the radio on MRO was working, and all the data that we had collected during the operations on the surface actually made its way down to the surface. So we actually have those products now. So what we've done now, since MRO is continuing to investigate what the problems are, is we have shifted. We have shifted our definition of which is the AM pass and which is the PM pass, such that each of the passes that we choose for those two activities during the Martian Soil will be Odyssey, since we know that Odyssey's radio has no issues at this point, while the MRO team works in the background to find out what's going on with their radio. Once we have established a good understanding of what the radio situation is, and it's what we would call reliable again, we'll go back to our nominal sequence. But this is a contingency that we had always planned for. As we said prior to landing, we had always identified the fact that we could operate this mission with either of the two spacecraft, and as it stands now, we're in fine shape. So bottom line is we're all doing well. The vehicle's doing well. We did good operations on the surface yesterday. We've uplinked the sequence this morning, and hopefully by tomorrow we'll be able to show you some deployed or partially deployed robotic arm images. With that, I'll send it back to you, Dwayne.
Thanks, Barry. And now I'll turn it over to Mark, who will again reveal incredible images. Mark?
Yeah, co-investigator responsible for the Surface Stereo Imager, SSI. One of the things I pay very close attention to is what have we seen. The first graphic shows my scorecard. This is Mars as we have seen it from SSI. This is a polar projection. The center of the image is where the camera is, and it's essentially looking sort of like a fisheye lens from above would show you the landing site. So you see from the lander at the center all the way out to the horizon and the sky in all directions. There's a lot of black space in here, and there's a lot of Martian terrain represented as black space. So my job is to fill that in. We hope to do a very good job on that in the Sol 3 afternoon coming up today. Starting from the bottom of the image is the site pan, a low-resolution black and white look at the landing site that we're taking in steps. That's the part that we acquired on Sol 1. Across the center at sort of the 9 o'clock to 3 o'clock positions are many lander images that we've taken to diagnose the state of things on the lander, starting with the solar arrays on Sol 0. And then as you go up from where the camera is close to the lander, you see the Robotic Arm Workspace, which I will come back and talk to later. At the 11 to 12 o'clock position is that Sol 0 panorama that we showed you. What I'm going to come to in just a moment is the part at sort of the 10 o'clock to 11 o'clock. That's what we got new as part of the run-out sequence that Barry mentioned. Our initial plan was to get the entire landing site at low resolution in black and white and then come back and take it at higher resolution in color and get to that as soon as we can. Turns out with the run-out, we actually got a head start on the color part. When we take color images with SSI, one thing we'd like to do is make sure we're showing you the right colors. So we actually fly little color calibration targets on the lander. This is an example of one, an engineering model that we have on the Earth. These were provided by the University of Copenhagen in Denmark with color chips from Central Florida University. And these are flying on our spacecraft for us to use as color calibration. So if we go to the next graphic, this shows 3 of them that we have. One of them we took color images during the run-out. The other 2 we only have black and white images so far, but we'll get many color images over the course of this mission. We have them in different directions so that there's always one close to wherever we're looking in color. One thing you'll notice on the 2 that are in black and white is that there's stuff on them. There are 2 grains on one on another in the sort of 2 to 3 millimeter size range. It seems that we kicked up some large particles on landing, and we've got a few of those on the deck. Actually, in the image on the upper right, you can see a few on the deck itself, plus ones on the calibration target. The calibration targets are actually have magnets protecting them. Martian dust is magnetic. So there are rings around the edges of these things that will collect dust, and then central areas that will stay clean throughout the mission. So the next slide is what this is all about. We take the color calibration in order to be able to show you the great pictures like the animation that I think will come up in just a moment. We looked at the Martian terrain to the northwest. We're going to look from the lander panning up to the sky. At the very bottom right of what we're about to see, we're getting close to, but not in the Robotic Arm Workspace, although this is an area that in test circumstances we have used as a place to dump material. The robotic arm can't dig here, but we can potentially dump stuff. We haven't made that decision. There's a trough running across the bottom here that connects with the trough in the workspace. and then a polygon that's coming into view on the top, sort of splitting actually into left and right. And then as we get further out, we're starting to see more of these. These are connecting with the polygons that we see in the MRO images, but the team hasn't finished really mapping all of these together. So I think that's work that will be shown in the near future. We also collected 2 more big rock sightings. So the small number of rocks you heard about is real. There aren't very many big rocks in that image or any of the others. But as you look into the distance, you see far more polygons. So we are trying to correlate those to what we see in the MRO images. So now I want to move to the lower right from there. The next graphic is going to go into the Robotic Arm Workspace. Managing this workspace is actually a very big deal for us. There's a limited area that we can actually access with the robotic arm and sample into the instruments. This area is a place that contains exactly what we were looking for in this mission. We have polygons that were formed by the action related to the ice that's under the surface. We have troughs in between those polygons, and they're all in a great area for us to dig. Now that said, I'm very optimistic about that. We're still investigating these things. We don't know everything there is to know about them. So as we pan through the workspace here, we're looking at an area, like I said, potentially where we might dump, and now we're panning in, getting closer into an area where the robotic arm can actually do its operations. We're starting to designate essentially our little national park system, or maybe a national preserve. A natural preserve is a better way of putting it. We are going to protect this part of Mars until we study it sufficiently that we can make wise choices about exactly where to do what. So we've designated some areas where it's okay for us to work. These areas are very small. We've designated some areas where we're going to keep it natural. We're not going to do anything. Now, we can't change the fact that our thrusters have modified some of this, but we're not going to do anything further to modify the terrain until we do understand it better. So if we go into the next graphic, it'll show a different representation of this area that might highlight some of the features we're seeing. The robotic arm, or the surface stereo imager, is a stereo camera. The view you just saw was a view through one eye, and it was perhaps a little difficult to make out where some of the troughs and polygons were. We take advantage of having stereo vision to get depth perception. And with that depth perception, we then feed that into a computer which manipulates the numbers all around and gives us a digital elevation model, a map of the elevation of everything in the terrain. What you're seeing is a color-coded map. Red is low areas, then yellow, green, and blue are progressively higher areas. So the red swath you see at the sort of 10 o'clock, 11 o'clock position coming in toward the lander is a trough between polygons. The yellow and blue and green areas are the polygons themselves. So basically, the robotic arm is shown in this graphic. It's not there. Bob will tell you about the status of it, but for the purpose of the model, this is actually delineating something for us. To the right of where the robotic arm is shown, going straight up in the graphic, that's our national park. We're not going to do anything there until we can come up with the best use of that terrain. To the left, there's not much terrain where the robotic arm can actually work, but there is a little bit that we think is accessible in that red, in the trough area. That's the area that we've defined as being acceptable for us to work initially. One advantage of that is that we can sample and we can dump without dragging the scoop across the work area. If you've ever been out digging, you know that when you go from digging to dumping, you can lose some material along the way. So we're not going to spoil our workspace. If we can go back to the image, as you go to the right from the robotic arm, the yellow polygon at the top, Humpty Dumpty, is one of our favorites because we can start at the top of that and cross down into the ridge with the digging. There's a rock at the bottom right end of Humpty Dumpty, King's Men. Just upper right from that, the reason I mention it, just upper right from that is the TECP preserve. The thermoelectric conductivity probe has a special area that we're going to preserve. We're not going to dig there. We're going to save that as a place to measure with the TECP. As you go across Sleepy Hollow, the red area between two polygons at about 1 o'clock, and come up that terrain, there's another rock, essentially to the upper left from where the SSI shadow is, that is called Headless. The second TECP preserve is to the upper right from there. So that's basically the workspace as we see it right now. We're going to try and learn a lot more about that and be able to tell you more about how it fits into the context of our terrain and what we might do in the future with our operations. But in terms of our ability to get started with the operations, Bob Bonnets is here to talk about the status of the robotic arm.
Thank you, Mark. Now, the first thing I'd like to do is to tell you a little bit about how the arm moves and what it's designed to do. I'm going to do that by demonstrating with my own arm. The real arm, of course, is quite a bit longer. It's almost 2.4 meters long and about 8 feet. So it has 4 joints. There's 2 joints at the shoulder. The first one is called the Azimuth Joint, and it moves the arm in azimuth from side to side in this fashion. There's another joint called the Elevation Joint at the shoulder, and that actually moves the arm up and down this way. One at the elbow, so it moves the forearm in this fashion, or like this. So it's in essence double jointed. It can do it in both ways. And then there's a joint at the wrist which moves the scoop in that fashion. And that allows us to move the arm out into the workspace, actually dig, dump soil, acquire a sample, move it back over on top of the lander, and deliver a sample to the instruments that are on the lander deck. If I could have the next slide, please. This is an image of the end effector of the arm, showing all the different tools that we have. The one I just mentioned, mainly the scoop there, that we use for digging and soil acquisition, but it also has on the bottom of the scoop a secondary blade that we'll use to actually scrape on the icy soil surface. At the back of the scoop, there's a rasping device. It looks somewhat like a drill bit, but the way to really think about that is it's a circular file. So as it spins, it will pulverize a little bit of the icy soil material and kick it up into the back of the scoop. Then we'll transfer it to the front of the scoop and move the sample over above the Tiga instrument or the mecha for delivery. The end of the arm also has the thermal electroconductivity probe that Mark mentioned that we'll insert into the ground to measure the temperature of the ground and also the conductivity. And finally on the forearm is the robotic arm camera. We use that to image the surface itself, but also to image the interior of the scoop. If I could have the next slide, please. So this was an image taken by the robotic arm camera of the scoop on Sol 1. As you can see right there, the scoop is essentially upside down. So when we have material in the scoop after we've acquired it, we'll be able to see what's in there. You'll notice a channel running down the center of the scoop, and that allows us to guide the material when we actually deliver the sample to the science instruments. Currently, the arm is still stowed in its launch restraints. That's to protect it during the heavy vibration and shock during launch, and also when we land on the surface. We have an animation of what we're going to do today, which is to unstow the arm from those launch restraints. It's secured in 2 places, one at the forearm and one at the elbow. It's actually folded up on the deck right now. So if we could show the animation there. If you look real close, you can see the scoop move back. That releases the pin on the forearm, and we raise the forearm, we move the elbow off the pin at the elbow, and then we move it out in a staircase fashion to get it out from underneath the biobarrier. So that's the planned activity for today, and it's obviously a very critical activity because we have to unstow from those launch restraints before we can actually do any of the arm motions to support the science investigations. Back to you, Dwayne.
Thank you. Thank you, gentlemen. Okay, we're going to now open it up for questions starting here in Tucson. And I'm going to ask if you can give us a little help here as we transition. Could you say the person's name that you want to answer the question, then give your name and affiliation, and then proceed with the question. Of course, wait for the mic. We'll go here with Eric.
Hi, Eric Hand with Nature. This question is for Barry Goldstein. Hi, Barry. So I just want to make sure I have this straight. Odyssey is now indefinitely doing both communication passes each day. How long do you expect that to be the case, and do you have any worries about Odyssey? It's a much older spacecraft. Are there any worries there?
Well, what you said is correct. Odyssey is doing the AM pass and the PM pass, and we'll keep that up indefinitely until we have utter confidence that we can rely on MRO being utilizing one of those passes. As I said before, however, we have not stopped communicating with Mars Reconnaissance Orbiter. We still will utilize those little passes we do all through the night to get engineering data up and back to Earth. So that's our plan. Now, you mentioned, do we have any concern with Odyssey? I'd like to remind you that Odyssey was developed at the same time that the hardware was built initially for this vehicle. We have utter confidence in the Odyssey hardware. It's the same hardware that we have on the surface communicating these great images to you as we speak.
Okay, I'm going to get ready to go to JPL unless we have one more question here. I don't believe we have any more questions here in Tucson, so can we switch over to the Jet Propulsion Lab? Any questions from the Jet Propulsion Lab, please? Okay, no questions. Let's, do you have a question here, sir? We'll come back here at Tucson.
For Barry Goldstein, Art Rothstein with the Associated Press. How soon do you anticipate that you will actually start experimentation by doing digging, actual digging?
I believe the earliest that we might be digging would be at the early to mid part of next week. However, we're going to take our time. The way things are looking relative to our energy on the vehicle, we're looking very good. We have more power than we had anticipated at this point of the mission. We're not going to rush anything. We're going to be very deliberate in our steps. Bob showed you all the steps we're taking today. We've divided the deployment of the robotic arm into 2 sols. We'll start it today, complete it tomorrow. We're going to take our time just to make sure that we do it right. So if it doesn't get done early part of next week, please be patient with us. We are going to do it. And as you saw from the images that we've had, those spectacular images, we've got a perfect workspace to do the science that's been projected for this mission.
Okay, we're going to, gentleman here.
Sorry, Aaron Mackey with the Daily Star, and this question is for Mark. I know that you said that this was done. The images that you took were sort of secondary because of the upload before. How long do you anticipate it'll be before you'll get a full sort of 360 view? I know it depends on primary missions and things like that. If you have any idea.
Right. I think we've got a couple milestones toward getting a 360 view. One is completing the low-resolution black and white survey. And that is something that actually the Part 2 of 3 and Part 3 of 3 were included in the Sol 3 plan, one before the nominal MRO pass and one right at the end of the day. So the shadows will be different, but it'll actually be a dramatic image. So we think we will have, give it another day or so after that to get the images down, we'll have a black and white survey. The color survey at higher resolution is something that we will be fitting into our plan in bits and pieces here and there. And I could imagine it taking a little more than 2 weeks, perhaps, maybe even into almost 3 weeks to get something like that down. And then we'll focus, from an imaging point of view, in addition to the support role, we'll focus on getting some even higher resolution and perhaps more colors of select targets.
Sorry, you said it's the low resolution today?
We're expecting the low-resolution panorama to finish today, Sol 3 on Mars, although not necessarily to a completely downlink today. So we would actually have it on Earth sometime tomorrow, next day.
Okay, we're actually going to wrap it up. This is an indication that things are going very well. We don't have any questions from the centers or on the phone. Please remember to go to the internet to get the latest developments and images. We will see you tomorrow, and as I say in Washington, I say it here, science never sleeps. See you later. Hello and greetings from the Lunar and Planetary Laboratory here in Tucson, Arizona. My name is Dwayne Brown with the Office of Public Affairs at NASA headquarters in Washington. And ladies and gentlemen, before we get started, it's my pleasure to acknowledge the incredible work being performed by everyone involved in the Phoenix Mars mission, especially the folks here at the University of Arizona. U of A is the first public university to lead and operate a mission to Mars, and the laboratory has been involved in numerous planetary missions. Quite simply, the Lunar and Planetary Laboratory here has the right stuff. So we have a lot of science, obviously, to get, but again, incredible work, and NASA is proud to have such an incredible team to work with. We have a very image-rich briefing today, so let me introduce you to our participants so we can get started with their presentations, and then we'll open it up for questions. First, to my immediate left, Peter Smith, Principal Investigator for Phoenix, and quite frankly, I've worked with a lot of PIs, and he is one of the coolest. Matt Robinson, Robotic Arm Flight Software Lead at the Jet Propulsion Laboratory in Pasadena. Jim Whiteway, Canadian Science Team Lead, York University, Toronto. And joining us at Jet Propulsion Lab, the one and only Barry Goldstein, the Phoenix Project Manager. And with that, I'll turn it over to Peter.
Thank you, Dwayne. Today is Sol 4. A Sol is a Martian day, 24 hours and 40 minutes. And we have a little saying in our group now that we're living on Sols. I'm not late, I'm on Mars time. And in fact, today we're definitely not late. Yesterday, Mark Lemon, our camera lead scientist, promised that by the end of tomorrow we'd fill in our entire panorama. He was wrong. It's been filled in as of last night, and today I'm going to show you the first look at the entire scene around our lander. And we'll be operating in this scene for the next 3 to 6 months. This will be an opportunity for us to take higher resolution pictures of various features that are of interest and to look at the full color spectrum that we have available with our camera. So let's take a look at some of the pictures. The first one is a fisheye view of the landing site, so you can see that we've completely filled in the surroundings around the lander. And to help you understand this picture, north is to the 12 o'clock position and the up position. And as we clock around to the right, we see the solar panels towards the east and towards the west, just exactly as we'd planned it 4 years ago. And as we look around at about the 7 o'clock position, we see a mast. That's our mast that holds temperature sensors and a wind sensor just at the very top of that little bump on the circle. And then at 9 o'clock position, we can see the robotic arm has moved up off the deck, and we'll hear more about that from Matt. But you can see the scoop right up against the horizon. It's blocked a little bit of our view of Mars, darn it, but that's okay, because it's going to be moving very soon. In order to get more of a physical sense of being on Mars, the next slide is going to take us on a little panoramic tour, and we'll start at north, and this panorama will take us around the entire scene as though you were standing on Mars and just turning your body and your head and looking around. So they're pointing toward the north, and now we'll start to sweep around towards the east and then the south. And what we notice is that we have a very hummocky terrain, and it's divided by troughs in between the hummocks, and there's just a few rocks, not very many. Most of them are kind of flat table-like rocks, and there's one down in the close-up view there. It's about 1 foot long. We see in the background, we can see our back shell and parachute. There's the scoop on the robotic arm and the camera to the left, and down as we get close to the lander here, you can see there's actually been some disturbances caused probably by the thrusters as we landed. So we'll be interacting in this terrain for, as I said, the next 3 months. But mostly we can only reach out and touch what the robotic arm can reach to, and that's the robotic arm is just a little less than 8 feet long. And so let's look at the digging space where that arm's going to interact, and I've managed to put some dimensions on the rocks that we can see there. Notice the camera seems to be dislodged from its mast in the shadow there. That's because it was taken at 2 different times. We take mosaic pictures. So this image is actually a mosaic of a number of little postage stamp-sized pictures. The rocks are a little more than fist-sized, 5 inches, and some are a little larger at 8 inches. These are not large rocks. We should be able to actually move them with our robotic arm and check out what's underneath. And as we scan across here, we can see that we have lots of places between the rocks where we can use our robotic arm and dig down under the surface and see if we can really find that ice layer that the Odyssey team promises is just under the surface here. But as you can see, there's a number of rocks, and in order for the science team to discuss the rocks and talk about them, we've given them a naming scheme. And the naming scheme, rather than being long numbers and letters, we've tried to make it a little more fun for our science team. And we're using the themes of fairy tale characters and folk legends. And so in the next slide, we've started with some naming opportunities. And one that came to mind right away was Humpty Dumpty. And we got the king's men and the king's horses. And pretty soon, oh, there's the wall. And notice it says National Park. All of these areas are being protected at the beginning of our mission. Protected so that we don't drop things on that area or disturb it in any way more than the thrusters already have, so that we can later go in and dig our trenches. So we'll be taking our first touch to the left of that line that says National Park. Also, we're using the theme of Sleepy Hollow because that's one of the troughs that cuts across our landing site. It's hard to tell here, but we have stereoscopic images that allow us to get an elevation profile across here. And since the legend of Sleepy Hollow involves a man that lost his head, we have Headless and Ichabod. And we're starting with the theme of Alice in Wonderland. So there's a rock called Alice, and we'll be developing more names as we go. But this allows the team to have a little fun with the naming opportunities, because we're going to use as many as 100 or 200 names throughout the mission, and it helps us remember what they are. And because the robotic arm is such a crucial and one-of-a-kind component on our mission, we don't have two arms, we only got one. We are so happy to be able to report today that the status is looking good, and to give that report is Matt Robinson to tell us about the robotic arm.
Thank you, Peter. Yesterday, we sent commands to the spacecraft down to the lander to unstow the robotic arm, and today I'm ecstatic to let you know that it was successful. The robotic arm is now unstowed. It's out of its launch restraints. Next, we'll take a look at some images from our stereo imager. These are images of the wrist. The robotic arm has two restraints. It has one at the elbow and one at the wrist. If you take a look at, if I use my arm as an analogy, we have the upper arm and the forearm, and we have our wrist here. To unstow from the wrist restraint, the wrist does a motion kind of like that, which is what you saw in the images that we just saw there. Okay, next up is a cartoon of what's happening up under the wrist. So as the wrist rotates, what you'll see in the bottom right corner, you'll see a pin. And that pin is going through a loop that's connected right here on our forearm. So the action of the rotation of the wrist causes a little hook right here to engage a cylinder, a spring-loaded cylinder, right there. So we have a motion here. It rotates the cylinder, and it unlatches that pin. That pin springs out of our loop, and the wrist is free. Okay. Next up, we have an image of our elbow, or a series of images of our elbow. And as has been documented in previous press conferences, one of our concerns, albeit a fairly minor concern, was the biobarrier. And you'll see in the initial image that the biobarrier is draped over our elbow partially. Well, that was a contingency that we were prepared to handle. And the way that we handle that is through a stair-step type motion. We move our elevation joint a little bit up, move our azimuth over, and then we repeat that, up and over. And at that point, as you can see in our images, we were completely free of the biobarrier, and we were unstowed. And this is great. It required all four of our joints to unstow the arm. Our arm was cooped up in our restraints for 14 months. It was raring to go. It's busted loose now, and we're ready to go. We're excited. So what's up next? So basically, the robotic arm looks something like this right now on Mars. Today we sent some commands to the arm to deploy it. And to do that, it's going to stand straight up like this. And have to be a little bit of an acrobat contortionist to do that motion. After we do that, we're going to do some more checkouts on each individual joint at hot and cold temperatures, hot and cold relative to Mars. And that's because the robotic arm is going to be required to move over a range of temperatures. What's up next? We need to determine before we touch the surface the stability of the lander. We have good SSI images of the nearest footpad, but we need to take a look at the other two in order to determine stability. In order to see one of them, we actually have to look up under the lander. Okay, but the SSI, before we do that, there are a couple blind spots that the SSI can't see. We don't want to just move the arm up under the lander. There could be a large rock there. It's doubtful that there's a large rock based on what we've seen, but we're not going to take any chances. We're going to position the robotic arm camera, take a snapshot, and based on that snapshot with the robotic arm camera, we can determine if we're free and clear to move the arm up under the lander. I can't stress enough that we have actuated all 4 joints. I've taken a look at the data. The robotic arm team has taken a look at the data. We've determined that the data looks very comparable to data during test runs here on Earth, which is very good. All the joints are healthy, and we're just raring to go. We're raring to go out and get a sample for Peter and the scientists and the science instruments. And with that, I'll turn over to Jim with weather.
Okay, thank you. So the first report that I can give is that the Canadian team is walking on moonbeams today because all 3 of our instruments that we've provided are up and running. And I can also then give the second weather report for the mission. And our pressure and temperature instruments are reporting that a repeating pattern with a high temperature of negative 30 degrees Celsius, which is negative 22 Fahrenheit, and a low temperature of negative 80 degrees Celsius, which is negative 112 Fahrenheit. And we can now add dust and cloud measurements to our weather reports because the LiDAR instrument is up and running. So this is at the heart of this system is a laser. It emits pulses of laser light up into the atmosphere and detects the light that is scattered back. So we can measure the properties of dust and clouds up to a height of 20 kilometers. So this was the most challenging of our instruments. For example, it has to be pointed with an accuracy of a few hundredths of a degree. So that's like shining a laser pointer at a baseball from home plate to center field. And that pointing had to stay in place from Ottawa all the way to Mars. And so we're very happy that it's still working. And we can report that we've observed dust being lofted up to heights of above 3 kilometers. And now we're looking forward to 3 months or more of investigating the Martian atmosphere. So now I'll pass it over to Barry Goldstein at JPL.
Well, thanks a lot. And first of all, let me say, Dwayne, that one and only is probably a blessing for all of the team. I think more than one of me would be a bit hard to handle for this team. But nevertheless, thanks for the compliment. Let me also point out, Peter and I were chatting just before this press conference started. We were talking about how even in our wildest dreams, things couldn't have gone as well as they have, not only from the engineering aspects of how the landing went, how the spacecraft is performing, how the payload is performing, but just look at that workspace. It couldn't be better. It could not be better. So I'm really looking forward over the next 90 sols for some major scientific breakthroughs. This will just be fabulous. That being said, I want to also make sure that everybody is aware that while we had a very exciting time on Sunday and we have been reporting on the various things that have been going on over the course of the last few days, they've been reported as anomalies and things that we've been working through. Everything that we faced over the course of these last 4 sols on the surface of Mars has been rather benign. The team has been really well rehearsed in terms of anomalies. Our capabilities have been exercised, and nothing we've done has actually stressed the team whatsoever. The team has been performing just remarkably, and none of these activities have been major. We've been trying to make sure that everybody in the media is aware of everything that's going on, so please don't misinterpret things that are rather minor in terms of things that we overcome as being major hurdles. This has been, in some regards, very, very easy. Speaking of the team, I would like to also point out we have a team, as Peter pointed out, working on Mars time. We have about 40 or 45 people from JPL who have basically wrenched their life up and moved out to Tucson to live in what's been described as perpetual jet lag. That's a very tough thing. Obviously, a lot more team members, the science team members, and many people from the Lockheed Martin team are also doing that. But I want to give special thanks to these guys who are basically working very weird off-hour shifts that keep rotating every day. Very tough thing to do. This includes the management team that's moved here from JPL to Tucson, as well as the operations team, and also the news team who are helping provide all this information to everybody. So thank you very much. Well, what I'd like to just finish off here from JPL and talking about is we have now achieved a major milestone for this mission. We had divided the mission, the surface mission, up to various phases. One phase, or the major phase that we're in right now, is called characterization, where we characterize both the engineering subsystems as well as the payload. Then we get into nominal science operations. Well, the characterization phase in itself is broken up into two pieces. One is engineering characterization, and we have, as of last night, with the removal of the robotic arm from its launch restraints, satisfied the criteria that we had identified as safe to proceed. We now believe that all the engineering systems are functioning appropriately, all the major deployments are behind us, and we're now in the next major subphase, which is the checkout of the payload instruments, which darn near all complete already as well. We're going very well. So we've far exceeded, traditionally engineers were rather pessimistic, but we've even exceeded our optimistic goals. So things are going remarkably well, and the team from Tucson will be reporting regularly from here on out, and want to thank everybody for their interest, and turn it back to my friend Dwayne.
Thank you, Barry. Thank you all. We will now open it up for questions, starting here. If you can please wait for the microphone, and please address your question to the appropriate person and give your name and affiliation, and person here at the front here.
Thank you. Sally Rail with the Planetary Society. For Peter, you've named a lot of these targets. What will you go for first? Do you have your eye on something in particular?
Well, the first thing is to characterize the arm's ability to touch soil and dig soil. And so as we're in our characterization phase, that is not part of our science goals. That's just arm testing and kind of making sure we're ready to go. And that'll be done outside that national park boundary. It's more of a Superfund site over there. And so we're allowed to mess that part up a little bit as we practice with our arm. And I don't know that we have a name for that place yet, but we're kind of over there in the theme of Humpty Dumpty, and so I'm sure the team will come up with a good name for where we first touch.
Any more questions here, gentlemen?
Alan Fisher with the Tucson Citizen. Peter, in terms of the characterization of the arm, have you completed the mock-up here in Tucson that will be used in the pit to help out with that effort?
I'd like to ask Matt to answer that question. He's been the most active arm person on the panel.
Your question is, are we finished with the mock-up here? As with many missions in the past, we'll probably be doing engineering model testing throughout the 90 days. I don't know if we'll ever be completely finished with it. What's up next is practicing how we acquire the sample, going through techniques on how to get the proper amount of sample, also how to deliver to the instrument. Our first instrument is going to be Tega, and exactly how do you deliver it optimally to nail the sample into the oven.
Any more questions here? I don't have any. Oh, we have one caller. Caller, you are on with your question.
This is Emily Loftawala from the Planetary Society. And I have two questions. My first one is, where are the rocks in the landing site likely to have come from? Are they local, or are they likely to be impact ejecta from elsewhere? And my other question is, I've been enjoying the pictures of the wind tail on the Raw Images website. I'm wondering if you could tell us if there's anything you can interpret immediately about wind speeds from those images.
Well, I'll try the first question. The rocks don't come with labels. It's a little hard to tell just where they came from. We're still in the part of the mission where we're just figuring out where they are. The science team is looking at the patterns of the rocks and how they're distributed among these hummocks and troughs, and to see if the ground circulates like it does in some polar regions on the Earth and actually orders the rocks into patterns around these hummocks. And the ground can actually have convective cells inside of it in these polar regions, and so sometimes the rocks can move. So we're still kind of examining that aspect, and since we only have these pictures since last night for some of the areas, it's a little early to talk about where they came from. And as far as the windsock, I'll let Jim answer that.
Okay, so the telltale is similar to a weather vane or a windsock. It's provided by Denmark, and it's basically a very lightweight cylinder suspended on a thin thread such that the wind will deflect it. And in the images from the SSI camera, we can see the deflection and estimate the wind speed. So it's been calibrated such that a deflection is related to the wind speed. So we had an image of the telltale on Sol 1, and we're able to estimate the wind speed as being about 15 miles per hour towards the northeast.
Okay, we're going to come back here. The gentleman.
Question for Peter. Art Rothstein with the Associated Press. Given that everything is moving so smoothly, are you still looking at a time frame of starting actual digging next week, or will it be sooner?
Well, remember, we had to lose a day because of the communication glitch in MRO that's still being worked, and that's slowed our schedule down a little bit. As you know, the robotic arm is sort of our pacing item here, and getting it unstowed, which we've done now, and then looking under the lander, which is going to happen the next day or two, and finally just doing some touch and motion tests on the ground leading up to the first sampling. All of this really is a day-by-day process that I think has been delayed by one day because of this communication glitch.
Okay, I believe we have one question from the phone.
Yeah, thanks. This is Kelly Beatty from Sky and Telescope. This is for Peter. The SSI has a whole bunch of different filters that you can use to characterize those rocks. Have you had the chance to use those yet? Is there anything you can tell us about the nature of the rocks? I realize it's a little preliminary, but are they volcanic, glassy, sandstone, what?
Well, as you might imagine, the science team is quite interested in that question. One thing I can say for sure is many of these rocks are flat, almost like paving stones, and that's certainly a clue as to their origin. Don't ask me what the origin is yet, but that's a clue, so I'll just throw that out there for everybody to consider in their own way. We do not have a full spectral analysis of any of the rocks yet, so it's a little early to say much about their composition. We are trying to gather that data. It's certainly high on our list of things to do because we do have the opportunity to put 12 spectroscopic filters into the front of the camera and get a little bit of a spectrum. And the spectrum may tell us whether these are the same type of rocks that we see pretty much at the 5 other locations on Mars where we've had landers, or is there something different about these. So the other piece of information we have is the rocks seem to be brighter than the surface rather than darker. So I'll let you put that in your box of clues too.
Do we have another phone question? Go ahead.
This is Emily Loftawala again from the Planetary Society. I'm wondering, I think that correct me if I'm wrong, the robotic arm camera is only one camera. I'm wondering if you can do stereo imaging with that camera by doing small arm motions. And my other one is just a comment. I want to thank the team on behalf of an international community of enthusiasts who are very thankful that all the images are coming out on the internet as soon as you receive them.
The answer to your first question is yes. So we can get stereo images by moving the robotic arm camera into two different positions and taking an image of the same site from two different angles. It works quite well. We have a nice visualization tool to give us a terrain map from that kind of image. So we'll be doing that as we dig a trench, and we'll be able to get depth in the trench and sidewall dimensions and that sort of thing. And you're very welcome. I think involving the world in this mission is one of my highest goals, and the way to do that is to not hold on to data and just send it right out on the web so everybody can enjoy it as we do. So we're very happy to do that and wouldn't do it any other way.
Okay, we're going to come back here. Do we have a question here? And then we'll begin to wrap it up.
Hi, Andrea Thompson from Space.com and Space News. I was wondering if you could tell us what time it is on Mars now to give people sort of a reference. And does when the Martian day starts sort of vary, because I know it's a little bit longer than our day.
Jim? Jim's our weatherman. I'll bet he knows the answer to that.
Well, we started similar to Earth time, and we've been moving ahead 40 minutes each day. So I think we're about 2 hours off Tucson time.
So it's 2 hours later?
Yeah. So we're working while the spacecraft is sleeping. And that's why we're working at night.
Okay, we're going to wrap it up here. I want to, again, remind you the latest updates and images are on the web. And congrats again to the international and national members of the Phoenix Mars mission. It's a testament of incredible work, and we've still got a lot of science, of course, to go. We'll see you tomorrow. Go Wildcats.
Good morning and good afternoon, depending on where you are. From the Phoenix Mars mission, Science Operations Center at the University of Arizona in Tucson, Arizona. I'm Sarah Hammond, Public Affairs Manager for the Phoenix mission. Well, today is Sol 5 for Phoenix on Mars. We have a number of presenters today on our panel who are going to discuss images and data returned last night and to look ahead to upcoming activities. So please let me introduce our speakers today. To my immediate left, Ray Arvidsson, the Robotic Arm co-investigator from Washington University in St. Louis, Missouri. William Boynton is Tega co-investigator from the University of Arizona. Mike Daly is MET Chief Engineer from MDA in Toronto, Canada. David Spencer is Deputy Mission Manager from the Jet Propulsion Laboratory. And Leslie Tampery, Phoenix Project Scientist from the Jet Propulsion Laboratory. And we're going to start with Dr. Arvidsson. Ray?
Hello, everybody. Well, we still very much like our landing site. You know, we brought you a place that was safe and in terms of not many rocks, big rocks, that was relatively flat, but we wanted a place that was scientifically interesting. And as you know, we touched down on a location that is just intensely dissected by pattern ground. And in fact, we're at a location where we think we can sample a polygon in a trough, and we're still evaluating that within the work volume. Now we've completed a 360-degree panorama called a side pan. The data were acquired on Sols 1 and 3. The terrain is so flat that what we're going to do is show you a movie in which we've taken the vertical dimension and stretched it out 8 times to see the horizon. So this is what the pan actually looks like with pieces of spacecraft, and you can see the pattern ground and the small rocks distributed throughout. But now what we're going to see is not what you'd see with the eye, unless you were able to stretch out 8 times. And there are no Himalayas off on the horizon. These are features that are kilometers away and that have relief only measured into 10 to 20 meters. So we're looking now off to the west, and as you know, about 30 kilometers away is the rim of this 10-kilometer crater Heimdall, but we can't see it because there's a gentle rise. But now we're kind of looking toward the south, and the feature that looks like it wants to be in the Himalayas is only about 20 to 30 meters high. And the parachute backshell and the heat shield impact site, those are, you know, a couple hundred meters or less away. And then we'll continue panning off to the right, And we've actually used the Mars Reconnaissance Orbiter context image data and HiRISE to identify those features and their distances. So the double peak there is more than 10 kilometers away, and we're looking at the meteorology mast sticking up. Those long dark features in the near field are small rocks. Here comes my favorite feature, actually two favorite features. That's the actual scoop, the ISAT, the Icy Soil Acquisition Device, but stretched out 8 times. And behind it, 5,000 meters away, is a gentle plateau that's filled with rocks. And that's one of the areas that actually showed up as a hazard in our hazard maps, but wasn't a big deal in terms of landing because of the small area. And then swinging around and then finishing off. So again, this is really stretched vertically so we could see the features on the horizon. Now we want to move into a much closer zone, and that, as you know, we've deployed the robotic arm, checked out the robotic arm camera, and we took a picture of the blind spot, that is the area the SSI can't see. So we see the footpad, which, as you know, is about 20 centimeters across, and pieces of the spacecraft. And if you look in the upper portion of the frame in the middle, there are those 3 tabular surfaces that are exposed. We don't know what they are. They could be exposures of ice, or they could be exposures of rock. What we have is what you see. So what we're going to do over the next few sols is go back with the robotic arm and the robotic arm camera and get closer in shadow and turn on the blue, green, and red LEDs so we can get some color data. So this is really scientific method. This is exploration and discovery. So we either have discovered ice or not. But what we want to do is go back and test this. And we have uncovered other areas on Mars during landings. The final slide is taking you back to 1976. Believe it or not, a picture I actually took. And this is Viking Lander 1. And we're looking at very close to the lander. The left side is the housing for the surface sampler arm. And if you look beneath it, that's where engine 2 has blown away some soil. And you can see that there's a crusty polygonal material underneath. That is not ice. That is duracrust. And we found by sampling in other places that it's enriched in magnesium and sulfur. So we've had some process where water is wicked up and left behind salts. So we have scientific method in front of us. We have 2 hypotheses. We have rock, we have ice. We're really pushing for ice, but we don't know if that's the case yet. And the real way to do this is to continue to look at this feature and then get out to the work volume and get the soil and expose whatever ice is underneath and see if we see a similar tabular shallow structure that we can sample and bring the material back into the spacecraft to really nail and test the hypothesis of ice versus rock. But this is pretty exciting because we expect ice only a few centimeters beneath the surface, so everything's consistent, but it could be rock. But remains to be seen in the next few weeks which is which. And let me introduce my partner, Bill Boynton, who will talk about Tega.
Yes, I'd like to talk about the Tiga instrument. Tiga stands for Thermal and Evolved Gas Analyzer. And what this instrument is a device that's actually going to analyze these ice or rock samples that we may pick up from the surface. Essentially, we put the sample into a very small oven. We close the oven, heat it up very carefully, and we look at any gas vapors that are given off from it. We have a device called an Evolved Gas Analyzer that looks at these gases, and by studying what the vapors are, we can tell what we put into the oven. For example, if there is any ice, we'll get some water vapor coming off at very low temperatures. And we actually do a process called calorimetry where we actually measure the amount of heat that it takes to warm the sample up. And if there's ice in the sample, it takes quite a bit more heat to melt the ice than it does just to heat up some dry dirt. So we're anxious to get on with measuring that. We did have a concern, though, in the data that came down yesterday. What we found was an anomaly that looks like we have a short circuit in the ion source. The ion source is a part of the Evolved Gas Analyzer that actually generates the ions that we analyze, and this short circuit is intermittent. We are working on some diagnostic packages that we'll send up in the next few days, And we're actually quite optimistic that we have a workaround that will allow us to operate the instrument with nearly the full capabilities that we had when it left the ground. But right now we don't know for sure, and it'll be some time before we actually get to the bottom of this. Okay, now I'd like to turn things over to Mike, who will talk about the meteorology package.
All right, I'm very pleased to report that the weather station had a very successful sol on Mars with a full sol's worth of high-resolution temperature and pressure data, and a 15-minute noontime LiDAR measurement, which is our second and longest. So if we could go to the first slide, we'll look at the weather report for today. Really, the weather is very similar to the previous day, except we have increasing dust activity, which is leading to lower visibility. So we have a high for the day of minus 30 degrees Celsius and a low of minus 80 degrees Celsius, or minus 22 degrees Fahrenheit to minus 112 degrees Fahrenheit. Pressure's at 8.5 millibars, and we had no wind measurements for the day. If we could go to the next slide. We have a very nice animation of the LiDAR to show you. This will show you the LiDAR in operation, and we'll move on to some data from there. You can see the optical components of the LiDAR are in that white shoebox-sized object. The dust cover opens, exposing the transmitters and receiver apertures, the smaller one being the transmitter, and you can see that the laser comes on, starting the measurement, and probes the atmosphere up to ranges of up to 20 kilometers, and it samples the atmosphere at 100 times per second in two wavelengths, one being invisible and the other being that brilliant green beam that was nicely shown in the animation. We can go on to the next slide. This is a camera picture of our instrument actually in operation on Mars. You can see that the cover's open and the instrument's taking data. This was a very proud moment for we Canadians, as Canada is so nicely displayed, and this is the meteorological station is our first set of instruments on Mars. So it was really a good day for us. Going on to the last slide, I'll give you a little example of some data that comes out of the LiDAR. This is really an evolution of the atmosphere directly above the LiDAR, and this is 15 minutes of data. It's a subset of the data we get back. And you're seeing data out to 5 kilometers, where the beginning of the measurement is at the left of the screen and the end is on the right. And the redder images are areas in the atmosphere where we have more dust scattering back more light into the LiDAR. So what's really interesting here is you can see there's actually an evolution of a dust feature given by the red at the lower right of the image as the instrument is measuring. And this kind of data we'll expect to see a lot more, and a lot more interesting features as we move forward with the instrument and get some measurements at different times of the sol as well. Okay. I'd like to pass on to Dave Spencer, our mission manager.
Thanks, Mike. Well, I'd like to describe a day in the life of surface operations. We're in Sol 5 now, and after 5 sols on the surface, the flight team is really starting to get into a rhythm. We synchronize our workday around Phoenix's workday on the surface of Mars. Just as Phoenix is finishing up its workday around 4 or 5 in the afternoon, the flight team is actually coming into the Science Operations Center here and gearing up for our night's worth of work to plan for the next day's activities on Mars. We start off with the kickoff meeting. We get the full team together in the big room and talk through the plans and objectives for the next day's activities. We also talk through any anomalies or issues that we need to work with, and this gets the team ready to go for the day. Then we wait for the downlink. Every afternoon, as Phoenix finishes its activities, it sends its day's worth of data from all the activities that it performed during the day up to an orbiter, either Odyssey or Mars Reconnaissance Orbiter, and that orbiter then sends the data back down to Earth. And for me, the best part of the day is when that data comes down. The science and engineering teams are in the work areas, huddled around their computers, and I'm generally out walking the halls kind of listening in terms of what's going on. Every once in a while, I hear a little eruption of excitement as a waited-for image, or if it's an engineer, a squiggly line comes down, and something that the team's been waiting for a long time, and that's really rewarding. Sometimes things get very quiet. The team will close the door if there's an issue that they've uncovered, and they get to work diagnosing it and come up with troubleshooting activities. So after the downlink period, we give the team a couple of hours to evaluate the data that they just received. We go into what we call a midpoint meeting, which is where we pull together the plans for the next day's activities on the surface. We start out with a template of activities that's been developed in the past. We're still in the characterization phase, so we've got very well laid out activities for each sol on the surface. But then we fold in the activities from the previous sols, including just recent information that we just got from the downlink. You've heard from Ray that we got this very intriguing image underneath the lander. We were able last night to schedule actually a duplicate image in Sol 5, which is going to be taken today on the surface, and that'll allow us to look for changes. If indeed this is ground ice, we'll be able to see any changes if indeed that ice is evolving on the surface. Last night we responded to the Tega anomaly by pulling out scheduled Tega activities from the plan, and that will give the Tega team a day's worth of work to come up with a troubleshooting path. We didn't want them to be bothered with analyzing and validating commands during the planning sol last night, so we effectively gave them the day off to work the anomaly. So once we have the plan established, then we go into an implementation phase, which starts late at night and goes through the wee hours of the morning. During this time period, the team's building commands, validating those sequences. We go through a very rigorous process of walking through these commands line by line to make sure that everything's going to work as expected when these commands are actually sent to the spacecraft. It's really a race against the clock because Phoenix is going to wake up on time every morning, and we need to get these commands up to an orbiter, forwarded on to the lander, so that when it wakes up, it gets its instructions for the day. And so far, we've been right on schedule every day. So for this day, which is Sol 5 on the surface, the centerpiece activity is actually using the robotic arm and the robotic arm camera to look underneath the lander, check out each of the lander legs and the foot pads to ensure that the lander is indeed stable. We need to do this so that downstream, when we want to interact with the robotic arm on the soil, that we know that the lander has a stable platform and provides that for the robotic arm activities. We're also taking more atmospheric measurements. We're taking some very precise images of a future dig site, which is called Humpty Dumpty. And all this data was going to be forwarded on to our next planning sols activities. And Leslie Tampery, our project scientist, is going to talk about our downstream activities.
Thank you. So yes, I'd like to tell you a little bit more about our strategic planning and what we have in the future coming up. Dave gave a very good description of the tactical process, and I'll tell you a little bit more about the strategic process and how that works. As you know, the first part of the mission is dedicated to checking out the instruments and doing our first touch of the soil and testing that soil and doing our little dig and dump. That will tell us something about the soil characteristics and properties, if it's loose consolidated or unconsolidated material, or if it's more hard and consolidated, and that will allow us to understand better how to dig in the future. So all of these activities are very important to us. In the very near term, in addition to what Dave mentioned, we're taking some imaging data to try to understand some of these potential test dig and dump sites so that we can check out how the surface materials look. And let's see. And we also are going to, of course, take more data of this feature under the spacecraft that Ray talked about that may be a rock or maybe ice, as was mentioned as well. So we have our strategic plan as well. So after the day's activities, when the commanding process goes off and the line-by-line checking process is going on, as Dave mentioned, the scientists go off and start strategic planning. So we're looking at refining the plan for the following sol, not the one we've just planned, but the following one, and then even sols 1 week to 2 weeks out ahead of us. So we have a strategic plan laid out now, out through about sol 22. And this plan is, we have a nominal plan, but obviously this plan has pathways because things will happen. We're designed to be discovery responsive. Our tactical and strategic processes will be able to be flexible and change as need be. So every sol, when we get the day's data, we not only evaluate it and say, do we want to execute the plan that we had laid out for today as planned, or do we need to make modifications? But we feed that information forward into the strategic process to modify downstream as well. So the upcoming activities are the test of the robotic arm, or the test, touch, and dig and dump of the soil, and also we'll be looking forward to actually getting our first soil sample. And we have a digging process that will allow us to and sampling process that will allow us to take a sample and deliver it to one of the three, or each of the three experiments, the Tiga that Bill was talking about, the MECA wet chemistry experiment, and the MECA microscopy. And we can choose to do those in any order that we want to. Again, our process is flexible. So at the moment, the first soil sample will be, in our plan, will be delivered to the MECA optical microscopy station. Excuse me. But as I mentioned, since our process is flexible and as we learn more information, we may decide to change how that works downstream. So I think that was all I wanted to say about that, and I'll give it back to Sarah.
All right. Okay, we'll go to questions first here in Tucson. As always, please wait for the microphone and state your name and your news organization. Andrea?
Andrea Thompson from Space.com and Space News. Was MECA originally scheduled to be the first instrument to be delivered to, or was that affected by the problems with Tiga?
Shall I answer that, Sarah? Okay. So yes, we did have Tiga in the plan, but we want to make sure that Tiga has adequate time to address their issues, and so we wanted to make sure that we don't slip our overall plan, so that we just rearrange things to accommodate.
Up here on the right, Leo. Kevin there.
Leo Enright from Irish Television. I have a related question and a follow-on, if I may, for Bill Boynton, I guess. As I understand, Tiga does a range of things, baking and sniffing in various orders. Can you explain where this ion source comes into that process? And can you say whether this affects the other geochemistry in any way, the MECA experiments, or is that entirely separate? And then I had a question about the dig and dump tonight. I mean, what time is that happening? And can you indicate where it's happening? It's obviously not going to be a national park, but I'm wondering where exactly is it going to be?
Okay, well, I'll address the first two. The Tiga instrument is completely independent of MECA, so there's nothing that we do that affects the operation of MECA. Now, the science that we get from the instrument is relevant to the data that we would get from MECA, and so they are somewhat synergistic in being able to reinforce each other. You asked about the ion source where we have the what looks to be a short circuit, and where that comes into this thing is when we're heating up a sample in the oven, we have a gas, we call it a carrier gas, that blows over the sample and actually delivers the gas to the evolved gas analyzer. The first thing the gas does, it goes into this ion source to be ionized and then accelerated by a high voltage to the detectors that actually allow us to determine what masses are present in this gas. And the problem there is in the ion source, in that one of the filaments appears to be shorted out. We do, on the other hand, have two filaments, and the first thing we're going to be trying is to operate it with the other filament and see to what extent that may solve the problem.
Dave, do you want to answer the second?
Sure. In terms of the dig and dump question that you asked, actually tonight when we get the downlink, we will have the data to make the lander stability assessment. Before we need that before we do the interaction with the soil. So the first thing that we do actually before digging is just a touch test. We go with the robotic arm scoop, touch the soil. We will be ready to do that once we make this engineering point. Are the scientists ready to interact with the soil? They want to make sure that they've completely imaged the site before we do the touch test, multispectral imaging. And so we'll have the debate in terms of whether the scientists are ready to do that or whether we need to go off and acquire more data. Sometimes the engineers say, come on, let's just get on with it. And sometimes the scientists say, we need more data. So we'll have that debate tonight. Once we do the touch test, then we do expect to go forward and do a test, dig, and dump, and then actually do a sample to deliver to the instruments.
Sally?
Hi, Sally Rail with Planetary Society. Either for Ray or Leslie, how soon will you go after this possible ice patch? Will that be one of the first?
Good question for Leslie.
Well, we're taking imaging data. The plan for this upcoming sol is that we'll take the imaging data of that during sol 6. But my understanding is that we can't actually reach that particular patch with the arm. So if it turns out to be ice or rock, we won't be able to actually acquire that particular patch with our arm. But we do believe that there's ice, a little ways below the surface soil. So it will be sometime after we get our surface soil sample, and then following on that, we'll start doing a trench. And then once we reach the ice, we'll be able to take a sample. So I can't say specifically when that will be.
Other questions? Alan?
I'm Alan Fisher with the Tucson Citizen. This question is for Dr. Boynton. The anomaly with the ion source, could that be related in any way to the moisture found during the flight to Mars that was resolved in the Tiga instrument?
No, those two things are completely independent. The moisture that we saw inside the instrument on the way to Mars and that we were very successfully able to remove is really a completely separate issue, and that essentially went away just by virtue of the times we baked out the instrument, essentially baking it out using a heater that was designed just for this problem.
Leo, another question here?
Thanks. Leo Enright from Irish Television again. I'm sorry for pressing this dig and dump thing, but could you just be a bit more precise about timetables? I know that's difficult, but I mean, will there be some touch test tonight? Will you be touching the surface tonight? I got the impression that you were talking about. Can you explain the sequence and the timing a bit more precisely?
I think I answered that as well as I could. The issue is, do we have the necessary data set for the science team to evaluate the composition of the soil so that we have all the information before we interact with it, and then we can do a comparison before and after. Maybe, Leslie, you'd like to talk about that comparison? Or?
Well, yeah, right now there's a debate between two different locations on the surface, and so we don't have enough information to decide which one will be a better location, or even if we want to go ahead and study both locations. So tonight will be the first, hopefully in today's downlink we'll be getting the first information on the first location, and that will guide us for the future. So yeah, I mean, again, our process is designed particularly to be flexible so that when we receive the downlink we can make choices responding to that. So that's one of the reasons we're not able to be very specific about how we're proceeding.
Well, Leo, the idea here is to keep the work volume as pristine as possible, and to think very carefully about what we're going to sample first. I mean, there are issues. I mean, if you do a dig and you then raise the robotic arm and you move it somewhere else, you're going to dribble some of that soil onto the surface. So it's likely that the dig area will be close to the dump area after we do the touch. We do a touch and then do a dig and dump. But we're debating now exactly where that should happen so we preserve as much of the work volume as possible without contamination.
All right, if there are no further questions as we sign off, let me on behalf of the entire Phoenix team send well wishes and safe travels to our friend Commander Mark Kelly and the entire crew of Space Shuttle Discovery as they prepare to lift off tomorrow for a rendezvous with the International Space Station. And because of the shuttle mission coming up, today is our last televised Phoenix briefing until at least Tuesday. So please watch the websites for information about upcoming briefings and for mission updates and new images. And have a great weekend.
Let's talk about one more thing. The scientists at NASA have been very, very busy. They've also been keeping tracks on the Mars lander. What's the latest there?
Yeah, interesting stuff on Mars. You know, of course, a week ago this time we were, biting our nails wondering if the Phoenix lander was going to make it to the surface of Mars. On Sunday, they successfully landed, sort of against all odds, a soft landing on Mars near the Martian North Pole. And the reason they wanted to go there was an orbiting spacecraft had detected through some of its sensors the presence of water ice in this Arctic area of the Martian northern climes. They landed there, and water is a big deal because wherever you look on this planet and you find water, you will find life. There is no exception to that we know of. And so the thinking is if you get to water on Mars, liquid or otherwise, you're a little closer to answering some questions about whether life existed there once before, or maybe, just maybe, in an underground aquifer where it's still flowing, maybe exists now. So what they discovered in looking at the pictures there that they've been assessing is they believe in the course of landing on those rockets, they kicked up an ice block. And there's actually a piece of ice that is sitting there on the surface. Now, the bad news is it's out of the reach of their scoop, which is only, after all, about 2.5 meters in length. So that's not good, but if there's one ice block out there, there's a very good chance when they dig down in their range, they might very well find the ice they've been looking at, put it in an oven, cook it, and who knows, maybe they might find some organic compounds, which, of course, are a building block of life as we know it. So that's pretty exciting stuff scientifically. We're going to be watching that one very closely. Could be some really fundamentally big news that comes out of this mission. You know, scientists don't like to hype it, but this could be a big deal. Aisha?
It sure could, and we'll have you monitoring it all for us and breaking it down. I'm Miles O'Brien. Many thanks.
Hello again from the Phoenix Mars Mission Science Operations Center at the University of Arizona in Tucson, Arizona. I'm Sarah Hammond, Public Affairs Manager for the mission. Well, we're ending our third week on the surface of Mars, and it's been kind of a busy week around here this week. We've been doing a lot of looking, we've been digging and scooping, we've been dumping and shaking and sifting, we've started baking. We're going to start sniffing real soon and also doing some tasting. And to tell us more about these sensory experiences today are Peter Smith, the principal investigator of the mission from the University of Arizona, Tom Pike, science team member for the optical microscope from Imperial College London, Mark Lemon, stereo surface imager lead scientist from Texas A&M University, and Milton Reno, science team member for Atmosphere from the University of Michigan. And Peter, why don't you lead off our discussion today?
Thank you, Sarah. Our last televised press conference was marking the end of our characterization period. That's the time we chose to test our instruments and to do our first touches of the soil and actually kind of get our calibrations all done so that we're ready for our science phase. Today is our first science phase press conference, and so we have a lot to report. The most wonderful news I can give you right away is that we have samples from the surface inside of two of our instruments, the microscope and the Tega. And today we'll hear about the microscope examination, but the Tega information will be coming shortly after. Not today, but next week. Just to recap, to get back to the big picture of this mission, our mission was inspired by the data returned from Odyssey spacecraft, and the Odyssey scientists, including our own William Boynton, told us that there was ice near the surface surrounding the polar caps. And so the Phoenix mission is specially designed to try and understand what is going on inside of this ice. This is important because on Earth, polar regions preserve traces of climate change and even signs of preserve signs of life and organic materials. So this is a really key place to look on Mars to see if the same thing is true there. On the Earth, we use very sophisticated instruments to do these experiments, and we brought similar sophisticated instruments with us to Mars to do this analysis. The orbiters have been very helpful in the process of getting us to Mars. We've had the Mars Global Surveyor and the Odyssey that have provided data sets that we use to choose our landing site. But it wasn't until we had the Mars Reconnaissance Orbiter with its high-resolution camera that we learned we had to avoid rocks. And we were very successful in avoiding rocks, as you can see in the pictures that Mark Lemon will show just after this. And this has been really useful for us because some of the regions in the polar, some of the areas in the polar region are extremely rocky. We also use our orbiters for communications, and really during our entry, descent, landing, we got signals back from both Mars Reconnaissance Orbiter and from Odyssey, and also from Mars Express. So the orbiters have been very useful in communicating our signals back to Earth, and in fact we're getting so much data back that we're getting about twice the data volume that we're told to expect, and this has caused some consternation among our team because you have to write sequences for all the data gathering that we do with our instruments. And these sequences take a fair amount of time. They have to be checked and rechecked. And so our team, who are working on the difficult Mars time schedule, which of course started at the worst possible time, at night shift, and has now progressed to graveyard shift, has left the team a little stressed and tired. So if you see some tired people around the building, you know that they're probably on Mars time. So for the first time since Viking, we have instruments that have samples from the Martian soil inside and are ready to start analysis. We are, excuse me, our results from these analyses are going to be used to inspire future missions that will come to Mars and hopefully take over where we leave off, because we're bound to raise lots of questions. Okay, the next thing I want to talk about is digging into the Martian soil, and this has been something we've been doing for the last week or so, and digging in soil has been, of course, one of our key activities, because we're trying to find an ice layer, which we're told exists. We see a hard surface underneath the lander, and now as we dig into the soil, we see a hard, bright surface right within just a few inches of the upper layer. And if I can show the first picture, that is our first dig test into the soil, and then next to it you can see flashing on and off is where we've done our sampling. So the first dig test actually disclosed a bright surface just a few inches down, 2.5 inches, and so we've taken our samples right next to that, and we've delivered those samples to our Tiga instrument and our microscopic instrument. But there's still some debate about that bright material, so in the next slide we can see what we've done very recently is to try and dig a little deeper in both of these areas, and we see the exposed ice. So this is, I'm sorry, this is the second slide, which shows the same two locations as it was sampled a few days ago. Now the latest picture will be the next one that just came down today, and that's not there it is. So that's the exposed ice, as just as we've seen it today, as we dug a little deeper into these two trenches. And now, not everybody is sure that this is ice, so there's been some debate within our team. And the debate centers around perhaps there's a salt layer above the ice, which would be very bright and white also. So we don't want to discount that possibility. And some people hold on to this theory and some don't. So we've had a fairly intense debate among the team whether that's ice or salt, but everybody believes there's ice near the surface. Whether that's it or not is the question. The other question is this thick ice that goes down deep beneath the surface, or perhaps this is a thin layer and we'll be able to scrape through it. So scraping with our tungsten carbide scrapers on the scoop is really a high priority for us. The next topic is delivery to the Tiga instrument, and my next slide shows the first delivery to Tiga, which was a big scoop full of material dropped onto the cell, and it stuck and would not go through the screen. And you could see it's laying there on top of the open doors of the Tiga instrument. The Tiga oven showed no response. We tried using our little shaker device day after day for 4 days, and after 7 shakes, if I can show the next slide, yesterday we were successful, and this is a picture showing that the material has slid down over the screen, sort of like going over a cheese grater, and some of the material has gone inside and has filled the oven. And we sent the commands for the first operation last night, but we don't have our data back yet, so we can't report on any results today. This will be coming early next week. So this is a very exciting time for us. We find the soil is very clumpy, it's very sticky. It's an unusual soil, not at all like the types of soils we've used in our tests, which work just fine with all the instruments. And so we've developed another method of collecting samples, and that is to tilt the scoop a little bit and then vibrate it with a little power tool we have on the scoop. So it vibrates it a little and it shakes some soil down, and it kind of rains down onto the screen or onto the delivery port. And we think this is the method we're going to be using from now on, and we'll hear more about that. So next week, pay attention. We'll have results from Tega, and we'll be delivering samples to our wet chemistry cells. And to show off to introduce my next speaker, I have a wonderful animation done by our co-investigator Eric DeYoung, and this will introduce our next speaker, Tom Pike. So let's watch the animation. Here we are from our launch pad, looking up at the brightest object in the sky, which, as we zoom in a little bit, turns out to be Mars. And we're going at an incredible rate of speed towards Mars in this animation, a little faster than the spacecraft, which took 10 months. And we didn't slow down quite as rapidly, but in any case, we're zooming in on our spacecraft on the polygonal terrain, and there's our Mecha instrument. And now a wonderful picture taken with the microscope. Tom, will you tell us about it?
Thanks very much, Peter. Yeah, this is the highest resolution image of the soil of Mars, and we're looking at a sample that was delivered using, well, a variety of sequences we had to have operating to get this soil in. This is the first sample delivery to an instrument inside a spacecraft since the Viking missions over 30 years ago. And we didn't know so much about the soil when we came down. The remote sensing satellite data told us a lot about the ice. It didn't tell us too much about the cohesiveness of the soil, and we've had to work that out as we went along. So if we go to the next slide, just to show you what we needed to do to get this soil into the microscope station. As we zoom in here, we see the microscope station, which shares its box with the wet chemistry laboratory. Those are the 4 cells on the right-hand side. And at the front, you will see a little U shape. And if we see right in front of me, we have a mock-up of the very same box. And right in a chute here, we have the substrates poking out. Now, these are what we use to capture the sample that we deliver to the field of view of the optical microscope. So during the delivery phase, the substrates are sitting outside of the box, and they're ready for the robot arm to deliver a sample. So if we go to the next image here, the next animation, we see that the way that we had the robot arm deliver the sample in this particular case was not just a dump of the soil as had been done with Tega, but a sprinkle. And we tested this. We took 3 days in testing how to go about this sprinkle so that we would just get, we were hoping, the right amount of material on. We wanted enough material for it to be representative of the soil that we're looking at, but not so much that we would completely cover the substrates and not be able to see the individual particle sizes. So the robot arm came over the top of the microscope box, and a vibrator that is inside the scoop, which is used for when we are actually digging into hard material to loosen that. We've been improvising with that to try and see that we get a good sample to us. So if we go to the next slide, this is what actually happened. And you can see the scoop there poised just above the chute. In fact, it has just delivered the sample. You can see on the top of the box the particles, somewhat clumpy, and then just below the broad white area in the middle of the chute, those are our substrates outside, and this confirmed that we got a good sample of Mars material. So that's how we get it onto the substrate side of the box. We now need to be able to bring that in front of the field of view of the microscope. And the next animation shows how we go about this. So we see the sample wheel in yellow sticking out of the box, and what we have to do, we have to rotate that round so that it comes round in front of the 2 microscopes that we have. Today I'll be presenting data from the optical microscope. That's the orange microscope on the right-hand side. So the wheel has come round, and then we can move the wheel into the focus position. Just in front of that orange optical microscope, we have the atomic force microscope that we hope to be bringing into operation in the next week or so. Okay, so on the next image, we can see what we have captured. So just to give, what we're seeing right at the bottom of that image are the shadows from the atomic force microscope cantilevers. So they're all ready for operation. We've multiply imaged those. And if we zoom into the particles that we've collected here, this is a particle about 50 microns across, about the diameter of a human hair, a little less than the diameter of a human hair. And we see that in this case we have both a greenish part of the particle to the top. The supposition at the moment that that could be olivine. We know we see olivine elsewhere on Mars, but at the moment we can only go by the color. Below that we see the very characteristic orange coloration that we see in the Mars soil. And if we move the camera just a little bit, the optical microscope just a little bit focused out from the substrate holding this material, we can see that that clump is not, that particle is a clump of even finer particles. And we see that in the background. Particles right down to the resolution of the optical microscope. So we're going down to the individual pixels, which are 4 microns across. Okay, there's some other particles of interest as well. If we look at the, if we zoom in to a particle which is in the bottom right-hand corner here, and this is a glassy particle. If we look at this more closely, you see it's more rounded, and this may very well be a volcanic glass. And it is quite possible, if we look at the full image again of our substrate, that what we are looking at here is a potted history of Martian soil. We have the hard particles, these black glassy particles that over millions, even billions of years have slowly been weathering down, becoming iron enriched, that gives the orange material its characteristic color. And we're seeing that process captured on the variety of particles that we're looking at the moment. Now, this isn't the first set of particles that we've been able to image. We already had our substrates out to just passively collect material that was kicked up while the Phoenix lander actually came down with its retro rockets, somewhat blasting the material into the air. And we were ready to capture that. And if we look at the next slide, we see a comparison on the left-hand side of what we caught during landing, on the right-hand side of what we've got from the scoop. And the scale bar at the bottom is 1 millimeter across. What we see in the dust fall is a whole variety of very fine particles, right down to this 4 micron resolution on the left-hand side. On the right-hand side, we have what the soil has looked like once we brought it in. We can see that we've indeed got just what we were looking for, which is this field of particles well separated so that we can say something about their shape. But very importantly, we see that the clumping that was very evident when we were digging at the level of the scoop in the few top centimeters of the soil is even repeated down to the tens of microns that we're seeing here. These are tiny clumps, maybe made out of thousands of particles apiece now. But there's cohesive forces. This is obviously a very sticky material right down to the finest scale. Okay. And finally, if we look at the next, we've got a whole variety of substrates that we look at. We look at 6 substrates at a time. And this particular substrate we fabricated at Imperial College in London out of silicon. And it is a series of holes and pegs of different spacing. And the idea of this substrate is that we are able to tightly grasp the particles for future analysis with the atomic force microscope. Again, you can see the shadow of the atomic force microscope beams at the bottom of that image. And so what we have on the third strip from the left is that we've been able to capture a very good variety of particles. These are pegs which are 5 micron spacing, just about the size of the larger Mars particles that we'd be looking for. And of course, we're very eager now to zoom in probably another factor of 40 times. So we can extend that animation a little further, Peter, in a week or so, and see not just what the particles look like as maybe a little fuzzy blob, but we'll be able to, we hope, look down at the detailed substructure of those particles and actually see below the resolution of our optical microscope. Okay. We now have Mark Lemon, who is going to be talking about what the stereoscopic imager has been producing from its look around the lander.
Thank you. The Surface Stereo Imager has been very busy every sol, helping to contribute to making Phoenix a success. The camera is a tool both for helping to guide operations. It provides sort of our hand-eye coordination. It helps us pick where to use the arm, what to do, how to sample. And it's the way that we survey the site and connect what we see to other things that we know. Peter and Tom showed examples of some of the images that SSI has taken in the course of guiding the operations. I'd like to show one more example. This animation came down today, earlier in the day, Sol 18, and it shows the robotic arm poised over the trench at the commencement of digging operations, and as this animation plays, it will... I'm sorry, I'm waiting for the animation to actually play. The animation, the dig occurred in 3 parts over the day. The Sol 18 was our first serious dig, actually using the RA digging commands as opposed to the sample acquisition commands. And those commands were issued 3 times in the course of the dig over a 2-hour period. During each of those 3 digs, the SSI took 7 images spaced out over the dig. So I think we'll just be able to show you later what is happening in the trench during that time. We use that to monitor how the trench evolves over the course of the dig. What stuff do we uncover and then bury? How does the ice change its appearance once the digging is over? I'm sorry, I shouldn't say ice, the bright material. And I think what we see in the animation is very intriguing, and in particular at the end here we see a fairly stable look to it. There are very, very subtle changes related to the changing illumination, but no other strong variation. And you can see that the RA is just whizzing by in some of these frames, so you see it blurred a little bit. So this is a very dramatic way, I think, to visualize what's going on Mars, what went on Mars just a few hours ago. So SSI, in addition to its operational role, is our tool for surveying the landscape. It's the camera that can sit back, look at everything in color. It has human-like depth perception. So we have been taking advantage of that and acquiring our high-resolution color pan. And I'd like to show you the scene that we saw on Sol 16. This is looking at the landscape toward the west. We use images like this to understand the landscape as a whole. We can zoom out to the horizon and see distant features that are observable from orbit. You can see the hills fading into the dust in the background, as well as a small number of large rocks. That is exactly what we expected to find in the area that we were targeting for the landing. You can see some of the polygons in the distance as we pan closer to the camera, but then this also connects us to the stuff that we're actually sampling. So you see here in the scoop the sample that on Sol 16 when this picture was taken was just about to go into the microscope. So the dirt that you're seeing there is the dirt that Tom just showed in the microscope. And that's the robotic arm camera poised looking into the scoop there, and the very slightly dusty solar arrays at the bottom of the screen. So a successful mission really requires understanding the context for all of the observations that we take. We are acquiring samples, putting them into the instruments, and coming up with a detailed understanding of a very small part of Mars. With the images, like the next one is another example, we can connect these small-scale observations to a larger scale. So this is showing a view to the southeast, and we can zoom in and see the kind of detailed features in our landing site. The rocks here have a very blocky texture. Just as a reminder, Phoenix landed in an area that was affected by the impact that created Heimdall crater. And You're seeing relatively smaller rocks, rocks up to ballpark of a foot across. We're not seeing the large boulders that we saw at other places that caused us not to land there. The rock in the right-hand side there, Toto, is very interesting to me with its flat top, sort of an icebergy appearance, although it is a rock. And then as we pan out, we get to connect to the site as a whole. This is where we start seeing some of the troughs. We see the rocks just perched on top of the surface there. And going further and further out, we're still seeing mostly smaller rocks mixed in with the polygons until we get to the greatest distances where we can see the horizon. We start seeing two larger boulders there. Essentially, we expected to see boulders of the meter-plus scale, about one per baseball field in terms of size. And then at the far upper right-hand side, you see a bright glint. That is actually the back shell. You see the gold foil on the inside of the back shell that helped us land here. One interesting thing about that is if you look at the back shell closely, there is no parachute visible. While the parachute is clearly visible from orbit, the parachute must be lying in one of the troughs and hidden from our view. It'll be interesting to see if the wind blows it around any, if it ever shows up from our point of view. The next panorama I want to show is part of a complete set that we're trying to take. Ultimately, we will have a 360-degree view of our site in full color and using our binocular vision, using both eyes of SSI. This one is particularly important because this section, which was taken in the evening of Sol 14, actually comes up near our workspace. So you're looking essentially 10 feet away from the lander right now, just beyond Humpty Dumpty National Park. And as we pan across, we'll actually be coming up onto the area just behind Humpty Dumpty itself. Right now, we actually started just past where the trench is. And then as we go down, or as we continue to go across, we'll get into an area which connects up with Sleepy Hollow. So we're connecting the polygons and the troughs that we're seeing in the broader site with the ones in our immediate workspace. So I want you to imagine now standing, crouching in this area that we're looking at. One of the things that we can do with SSI is not only take color images, we can take stereo images. We take advantage of the camera's binocular vision, and we can use our depth perception to model the landscape. So the next graphic shows the landscape modeled. Right now it's only in black and white, but it shows this small section of Mars, and we're actually crouching down where we were just looking before in the color panorama and kind of turning our head around. You can see some of the polygons and troughs, the little hilly texture that you see. These are only about 8 inches tall, but if you sort of imagine yourself crouched down, they start to look a little more dramatic and impressive. I think this view is excellent. This is the sort of thing that we're trying to build up for the whole site. By the next week or two, we should have completed our mission success panorama, the panorama that we want to take to show from the spacecraft out to the horizon in full color and stereo, so that we can show an image like this, only in color, and fly around the entire landing site. So that's something that we're about halfway done with right now. We started on Sol 13, and through about Sol 18, we're about halfway done. So now, the last thing I want to mention that SSI does, we've been spending a lot of time looking up at the sky. SSI helps with the weather monitoring. There's a lot of dust on Mars, and we're measuring the amount of dust in the sky, and we're measuring the winds and seeing how the winds are blowing the dust around. And to talk more about the weather and how we're looking at it, here is Nilton.
Thank you, Mark. Phoenix is also studying then the weather and the climate in the polar region of Mars. And in order to do this, Phoenix has a meteorology station and a LiDAR that were built by the Canadian Space Agency. It has a mass spectrometer that's being used to measure the composition of the atmosphere. And it has 2 cameras that are going to be looking at the atmosphere and around near the surface. And it has a few other instruments, including the microscope that Tom Pike talked about. With the microscope, we'll look at the dust particles, including the particles that are raining out from the atmosphere. And can I have the first slide? So in the first slide, we have, for example, the weather report from yesterday. The temperature at the landing site has been between minus 30 degrees Celsius and minus 85 degrees Celsius. So it's really cold compared to the Earth, even the Earth polar regions. The pressure is very small. Like yesterday was 8.35 millibars. On Earth is 1,000 millibars. So it's a very small fraction of what we have on Earth. And the wind in the landing site has been pretty calm. Like yesterday was 14 kilometers per hour or 8.7 miles per hour. And we haven't been seeing too much in the action in terms of dust storms. But there is lots of dust in the atmosphere. And in fact, the atmosphere of Mars at the landing site has been like a really polluted place on Earth with lots of fine in the air. So decreasing the amount of solar radiation reaching the surface by about 10%. Can I have the next slide? So in the next slide, we show a little dust storm downwind of the landing site. Okay, this one shows 3 big dust storms over more or less the place where we landed. And those are very common both at the beginning of the spring and at the end, towards the end of the fall. So we expect to see some of those at the landing site, hopefully at the end of the mission. Some of us will be very excited about making measurements in those conditions. And the amount of dust will be so much that the surface can get really dark. Less than 10% of solar radiation might reach the surface. So, and I have one more slide. Okay, this one is showing a regional dust storm. We have been seeing lots of those, and it's close to a really deep valley in the ice there that's 3 kilometers deep. So it's the cold air rushing down this canyon and lifting dust downwind of Earth. And that dust is swirling around and moving around the planet. And where we landed is quite safe because it's upwind of this region. So all this dust is moving away from the polar cap and away from the lander. And as you can see, really around the polar cap is very windy. The dark areas that we see there are sand dunes. So there's lots of sand dunes around the polar cap. So I have one final slide too. Okay, this one was made by Mark Lemon with the camera. And it shows on the left is just the background sky that you can see is sort of dust when we look vertically with the camera. And the one on the right is a stretched version, and also its difference between sequence of images, and show us the dust moving with the wind. So we haven't been seeing any big dust storm, but we have seen lots of dust moving with the wind. So it's regions of more or less dust content moving, like what you would see outside in Tucson at this time of the year. Now to finish talking about the weather, what's really important is that in atmospheric science we cannot do controlled lab experiment to test theories and our understanding of our own atmosphere. But we can go to other planets like Mars and make measurements there and test the theories that we have that are sort of tuned with our bias towards what we understand of the Earth's atmosphere. So it's really important to go to other planets, especially Mars that has a much simpler atmosphere without too much clouds and without ocean. And another really good thing about Mars is that there's lots of dust in the atmosphere there, and we don't understand how dust gets from the air into the atmosphere and how it interacts with climate. In fact, this is responsible for one of the largest uncertainty in global climate prediction today. So we are going to learn a lot with this mission. I'm really excited to be part of it.
Okay, thank you, Milton and panel. We're going to go to questions. We're going to start here in the theater. Please wait for the microphone and say your name and your organization. Back here, Alan.
I'm Alan Fisher with the Tucson Citizen. This question is for Dr. Pike. You mentioned when you were looking at some of the close shots from the MECA optical microscope, particularly the black glassy material, that you felt that showed that material had been weathered. Are you able to determine if that weathering is from wind or from past interaction with water?
Well, the black glassy material will slowly wear away from the outside, its outside surface, and that can be for a number of causes. It can be just from being jostled around within the wind. It can be because there is water on the surface. Now, when I say water on the surface, that doesn't necessarily mean it has to be at the bottom of an ocean or on a beach. This can be just the merest surface monolayer of water that might come from the ice underneath, and that will slowly work away. We're looking at dust that has been around for up to 4 billion years, and so even the slowest process can wear it right down to this very fine reddish material that we end up with. It's very difficult to say definitively with the resolution that we have as to what that process is. We hope when we go in with the atomic force microscope that we will get better clues, because we'll be able to look at the individual particles and at the surfaces, and that may give us a better indication of what at the moment is a pretty open question.
Just to be clear, at this point with the optical microscope, we're not able to make that determination of whether it was wind or whether it was water that caused the weathering.
Up to this point, we haven't been able to make a definitive confirmation that water has been involved.
Thank you, Tom. Is there another question here in the audience? Right here? Go ahead.
My name's Deanna Morgan with Fox 11 News. I was wondering, what will it take to find out what that bright surface is, whether it's salt or whether it's ice?
We need to gather a sample of it and put it in our instruments. They're specifically designed for telling us what the material is. The Tiga instrument is very sensitive to even slight amounts of water, and if it's a high concentration of water, then they'll tell us exactly what the fraction of water to soil is, and the MECA instrument will tell us if it's salt. So we have just the right instruments on the surface here to answer those questions.
Thank you, Peter. Go ahead.
I also wanted to know, it was mentioned that there would be, and maybe it was meant to be a joke, but tasting. Will that actually happen?
Well, you could think of the wet chemistry cell as kind of a laboratory tongue, if you like. It's it can taste salt, it can taste acidity, and while it doesn't look like a tongue, it kind of acts like one, and will send us the signals back so that we can make a material just like that, and we can literally taste it.
Thanks, Peter. Another question here? Or let's go to the phone then. Is there a question on the phone?
Yes, my name is Jim King from Times, West Virginia.
Go ahead.
Okay. Would the most common soil, for example, at the Spirit site, be a close approximation to the soil we're seeing at Phoenix due to global wind transport?
Yes, I think that what we're seeing more and more confirmation of is that the soil and the dust that is settling out are really one and the same material when you get down to the individual particle sizes. What we are seeing at this particular site, though, is how the particles have adhered together, how they've clumped up. And that does appear to be more site dependent. So, yes, we're seeing that we probably have at the particle scale a sampling of the whole of Mars in just one microscope slide. The weightings may be a little different depending on what site we're at, but we're seeing indications. For instance, the olivine may not have come from nearby. It may have come from thousands of miles away and have been lofted and brought to mixed up with the more generalized reddish material that we're seeing everywhere.
Thank you. Is there another question online?
Am I online?
Go ahead. Speak up.
This is Dave Perlman at the Chronicle.
Go ahead, Dave.
The question, there's a difficulty here simply between watching it on the screen and listening. But anyway, I'm trying to find out what the significance of those volcanic particles are, the black particles. Maybe somebody could talk a little bit about what kind of evidence that provides as to past environments because of the degradation of the volcanic stuff.
Yeah, the glassy particles are probably what the soil would start from. If we could turn the clock back to when we first had erosion of the volcanic eruptive material, the magma that comes out onto the surface, it would break down into these glassy particles. It would be produced actually directly from the eruption. And we see from far away, from remote sensing, there is a lot of evidence of glassy particles everywhere. But this is the first time that we've actually been able to image them this close up as individual particles. So that is the starting point. We know that Mars has then had these billions of years to weather the material down. And at the same time, new material is being revealed. So you see a continuous process captured at any one point from relatively unweathered material, this glassy material, to this much more weathered, degraded, chemically altered material which is iron enriched and which forms the majority of the particles that we're looking at.
Thanks, Tom. We have another caller on the phone line. Go ahead, please.
Hi, this is Ann Ryman with the Arizona Republic in Phoenix. I had a question about, you mentioned this is the first time in more than 30 years that you have Martian soil inside scientific instruments. Could you just clarify the difference between what this lander can do and what the rovers did?
Sure. The rovers were specifically designed to study rocks. And in looking at rocks, they could understand the ancient environment in which those rocks formed. And so the rovers were given mobility in order to get to the rocks and remote sensing equipment in order to find the rocks. So their role was to find interesting rocks, go over to them, kind of grind off the outer surface layers, it could be a weathering rind, and then put instruments against the rock and measure their composition and take a microscopic image of them and do some remote sensing with infrared spectrometry. So those are the kind of things they're able to do. The difference with Phoenix is we're able to actually get soil and ices off the surface, and this is a more active, younger surface, and put them into very sophisticated instruments that can modify those materials in a way that we can understand the minerals, the chemicals, and the microscopic shapes and sizes of these particles. So there's quite a bit of difference here. I think the MER rovers are looking at ancient Mars inside of rocks, and we're looking at modern Mars in the soil and the ices.
Thanks, Peter. Another caller on the phone lines. Go ahead.
Hi, this is Ken Kramer for Spaceflight. Can you hear me?
Yes,
Sure.
yes.
Yeah, hi. I'm just wondering, you mentioned that these are volcanic, and I guess I thought you were going to be surprised if you saw volcanic material there. So are you surprised, and what is that telling you?
Well, we've seen, well, rather from remote sensing, we have seen that there is this glassy material quite commonly seen around Mars. So we're not surprised. I mean, one of the things that we can do with a microscope, as you can see, we're spreading out particles over a large field. So one individual particle may be 1 in 1,000 of what we're looking at. So we're able to look down at rather very small percentages of what might be making up the overall soil. So just being able to spread out the particles means that we're able to differentiate a lot of the processes and a lot of the stages of the particles that are taking place. So we're not surprised to see volcanic material. We know that essentially that's where it all came from originally, and we've seen this from remote sensing. What is new is seeing it at this resolution and seeing the individual particles.
Thanks, Tom. I believe we have one more caller with a question. Go ahead, please.
Hello. This is the Times West Virginian. Regarding Tega, is it possible that the screen is filtering out material with the cohesive properties, thus biasing the sample?
Well, it's hard to tell. You don't actually see the material that goes into the Tega oven. The particles have to be smaller than the screen sizes, but if you looked at the microscopic images and saw the 1 millimeter scale bar, that is the size of the openings in the Tega screen. So you can see the particles are all much smaller, much smaller than that screen. And it's the clumping and stickiness of these tiny particles that prevented it from going through. So I suspect, as you might imagine, as the dam broke and the particles all of a sudden careened through the screen, that you would get a mix of all the different types. But I can't positively say that, but that's my suspicion.
Thanks, Peter. Is there another question here in the theater? Alan, go ahead.
I want to direct this to Peter, please. In terms of the dig, that's the ongoing extension or deepening of the trenches, where does that stand in terms of reaching to the hard, solid feature that we were hoping to? Is that an ongoing effort, and will we be seeing that soon?
Well, if you look at the trench picture that I showed, and the one that Mark was showing, his little animation, you could see what looks like choppiness. It's like you're using the blade of the scoop to drag across the ground, and if it's a very hard material, it'll chatter.
and you can kind of see some chatter marks there. So this is hard material. There's no doubt about it. We would like to really test the hardness by using our scraper on it next. So that'll be happening over the next few days. I don't know exactly which day we'll do it, but sometime in the next week. And that gives us more purchase on the ground, and we can really apply more force and a stronger material to it. So if it's a thin layer, we should be able to crack it open. If it's a very thick layer, we might be able to scrape down just a few millimeters.
Go ahead.
No, everything that you all are presenting is very exciting and new. I'm just wondering if there's anything in particular, whether it be from the weather or the images or the soil, that stood out in your minds as being maybe exceptionally intriguing at all?
Well, I think I would say what's really impressed me about the landing site is looking around the site as a whole with the color images. It's all Martian yellowish red. It's the same color that we expect from the other sites. When you zoom in, everything is just different brightnesses, but the same basic color. And in this, utterly Martian landscape, when we dig just a couple inches down, all of a sudden we see something that stands out more than anything we've seen from a Mars lander before, in terms of the imaging and the color difference. So that impresses me with how much it just shows off how unique and interesting this stuff is.
All right, go ahead. Sorry, no.
A comment from the weather. What was impressive is how well mixed the atmosphere is. Like the dust is very well mixed within the first few kilometers of the atmosphere, and how much the temperature has been changing, and the amount of dust sort of constant since the beginning of the mission. Okay.
Peter or Tom, do you want to add to the discussion?
Well, I think that partly it's just zooming in at this length scale that we haven't seen before, seeing the particles, the individual particles that we knew were there. We knew that they had to be very fine from the scattering experiments that we'd seen. But this is the first time that we've been able to see them against a background, do particle size distributions, and start to put data in at the bottom of the length scale for another planet. The first time that we've reached down to this level.
The thing that impressed me was looking down at the lander leg and seeing what looked like exposed ice, something called snow queen, and then looking under the lander to the holy cow feature. This was truly a surprise to me, and one thing I love is that we get a close-up picture of that first exposed ice. I think it's called Snow Queen, is it? Snow Queen, and it has all kinds of modulations in it. There's little pits, there's a little what looks like a crack, there's level changes. It's not just a flat sheet of ice at all. It's got structure. What's causing that structure? So I think before we end this mission, we're going to pretty much lay waste to our national park system that we've developed, and we're going to expose this ice table as much as we're able with the arm, and we're going to look at the shapes underneath the soil that can't be seen from orbit or even from Mark's camera without using the arm. And this will be new territory for to explore, and something wonderful is likely to come out of it. So stay tuned, and we'll see what's under the surface. We'll peel back the surface layers.
Thank you, panel, for today. Thanks for the questions. Before we sign off from Tucson, I want to wish all the gentlemen a happy Father's Day this weekend. We'll talk to you again next week, and until then, please continue to check the several websites for updates on the Phoenix Mars mission. Talk to you soon. Thanks.